In the name of God, Fluid Mechanics, Chapter 8, Potential Flow and Computational Fluid Dynamics. From Frank M. White, 7th edition. First we have a motivation. The basic partial differential equations of mass, momentum, and energy were discussed before in Chapter 4. A few solutions were then given for incompressible viscous flow. Also in this chapter, in Chapter 4, the viscous solutions were limited to simple geometries and unidirectional flows, where the difficult nonlinear convective terms were neglected. Potential flows are not limited by such nonlinear terms. Then in Chapter 7, we found an approximation, Patrick boundary layer flows, onto an outer inviscid flow pattern. For more complicated viscous flows, we found no theory or solution, just experimental data. The purposes of the present chapter, Chapter 8, are 1. So, the main purposes. Excuse me. One, to explore examples of potential theory. Potential theory examples. To indicate some flows that can be approximated by computational fluid dynamics. Indicate some flows that can be approximated by computational fluid CFD. The combination of these two gives us a good picture of incompressible flow theory and its relation to experiment. One of the most important applications of potential flow theory is to aerodynamics and marine hydrodynamics. First, however, we review and extended the concepts of fluid dynamics were discussed in previous chapter, especially in Chapter 4. So, introduction and review. Consider this figure. This figure reminds us of the problem to be faced. A free stream approaches two closely spaced bodies, creating an internal flow between them and external flow above and below them, which is shown also here in we see internal core and inviscid external flow. The front of the bodies are regions of the favorite gradients, decreasing pressure along the surface, rate, gradient, and boundary layer will be attached and thin. Inviscid theory will give excellent result for the outer flow if Reynolds for outer flow. For the internal flow between bodies, the boundary layers will grow and eventually meet, and the inviscid core vanishes. Inviscid theory works well in a short duct where if the L on D equal smaller than 10, such as the nozzle of the wine tunnel. For longer ducts, we must estimate boundary layer growth and cautious about using inviscid theory. For the external flows above and below the bodies as shown in this picture, inviscid theory should work well for the outer flows until the surface pressure gradient becomes adverse, increasing pressure. For outer flow, let me write for internal and for outer flow. Inviscid theory should work well for the outer flows until the surface pressure gradients becomes adverse. Increasing pressure dP on dx, and the boundary layer separates or stops. After separation point, boundary layer theory becomes inaccurate and the outer flow streamlines are deflected and have a strong interaction with the viscous near wall regions. The theoretical analysis of separated flow region is an active research area at present. Review of velocity potential concept as we explained it in before. For a streamline and potential velocity we have relations. Let me write review of velocity potential concept. Recall from the previous section that if viscous effects are neglected, the velocity potential are available when the flow is laminar and inviscid. Viscous effects were neglected. Low speed flows are irrotational. So we have irrotational case and the velocity potential phi exists. So we can write this relation for V, or we can write U. The continuity equations. So let me write again. The continuity equation is for inviscid and irrotational flow. We have this relation for continuity. So we can write del to phi equals to 0. So we have this relation for continuity as a function of potential, velocity potential, which is the continuity equation. And for momentum equation also we have the relation based on the potential, velocity potential, which is constants where the typical boundary conditions are now free stream condition. Outer boundaries we have for outer boundaries on phi and are now as boundary conditions, and the velocity normal to the boundary at the body surface also on where n is perpendicular to body. Unlike the no-slip condition in viscous flow, here there is no condition on the tangential surface velocity. So in this case there is no condition on the tangential surface velocity. on S. S is the coordinate along the surface. This velocity is determined as part of the solution to the problem. Occasionally, the problem involves a free surface for which the boundary pressure is now n equals to Pa, usually a constant. The Bernoulli equations then Bernoulli equation. We have a relation for Bernoulli equation in momentum, which was on phi on rho t plus the Bernoulli equation then supplies a relation at the surface between V and the elevation Z of the surface. For a steady flow, we have this relation for minus 2gz surface. It should be clear to the reader that this use of Laplace equation with now values of derivative of phi along the boundaries is much easier than a direct attack using the fully viscous Navier-Stokes equation. The analysis of the Laplace equation is very well developed and is termed potential theory, with whole works written about its application in fluid mechanics. There are many analytical techniques, including superposition of elementary functions, conformal mapping, and numerical final difference, numerical final element, numerical boundary elements, and electric or mechanical analysis that are now outdated. Having found the velocity potential from such analysis, we then can compute the velocity vector v. We have also a review of a string function concept. From previous chapter 4, if a flow is described by only two coordinates, the string function psi also exists as an alternate approach. Two coordinates described for two we have the string function psi exists as an alternate approach for plane incompressible flow in, for example, xy coordinate. We have u and v minus the condition of irrotationally reduces to Laplace equation for psi. this condition which give us this relation. The boundary condition also for free stream are now and the boundary condition, right? And for solid surface, as also boundary condition. The second boundary condition is partially interesting because any line of constant size in flow can therefore be interpreted as a body shape and may lead to interesting applications. Any line can be interpreted as body shapes. For the application in this chapter, we may compute either phi or psi or both, and the solution will be an orthogonal flow net. Once found, either set of lines may be considered the phi lines and the other set will be psi lines. Both sets of lines are Laplacian, could be this picture shows us an example for velocity potential and streamline in a flow where in each point the phi and psi are perpendicular to each other. We have also plane polar coordinate for potential flow and streamline plane polar coordinate. VR equals to and B theta then Laplace equation is have in correction here. Laplace equation Exactly the same equation holds there for the polar coordinate for note that psi is 2D function and it's applicable in 2D problems. The next section in this chapter is about let me write an intriguing base set of potential flow with no free surface is that the governing equations, as said before, contains no parameters nor do the boundary condition. The next section is elementary plane flow solution. We'll discuss it in next video.